Now that we have seen what DRAM looks like, let's briefly look at how to connect the DRAM to the processor. So we have our processor. It sends its requests to level 1 cache, which sends its misses and write-back requests to the larger level 2 cache, which might send its misses and write-back requests to an even larger level 3 cache. And let's say that these are all on our processor chip. Now what happens is the misses and the write-back requests from the L3 cache would be made over an external connection. So we need processor pins here. And traditionally, this data would go over what is called a front-side bus. Now, you want to design the processor chip so that you can connect it to many possible memories. So you don't design the front-side bus such that it supplies the row address and the column address and so on to the memory chips. What you have instead is another chip that contains the memory controller. And that memory controller will have what's called a memory channel connecting it to a DRAM module. And over this channel, it will issue things like open a row, read something, get the data, write something, supply the data, close a row, open another one, and so on. And it will usually have more than one such memory channel. So the memory latency, as seen by the level 3 cache, is not only the access time of the memory array here. It includes sending the request over a front-side bus, having the memory controller figure it out, sending the page open to the appropriate DRAM, sending a request to read, supplying the column addresses and everything, getting the data over the memory channel. Note that you have a level 3 cache miss. That means you want a whole cache line worth of data to read. So it takes a while to transfer that data here. Then the memory controller reads it from the memory channel, which usually has one bus frequency, and sends it at a different data rate over the front-side bus to the processor chip, which then puts the line together and puts it in the L3 cache. So the latency includes all of this here in addition to just the memory access. And this can be a significant part of the overall memory latency. So recent processor chips integrate the memory controller, which means that the memory controller is put on the same chip as the processor and the caches. Now we no longer need the front-side bus. We can use lots of on-chip wiring to communicate with the on-chip memory controller. So this can be plenty of bandwidth and very, very close. This whole thing is something like 2 by 2 centimeters. And then we just send requests directly through the memory channels to DRAM. So now the processor chip directly knows how to talk to DRAMs and open pages and so on, which dramatically can reduce this part of the latency. And because it's not a negligible part of the overall latency, we get our data from DRAM a little bit faster. Actually 10, 20, maybe 30% faster than before. But the cost of that is that now we designed a processor chip to talk to a specific kind of DRAM. And because of that, we need a relatively high degree of standardization of DRAM modules. So that, for example, when we go from 2 GB to 4 GB memory modules, we don't have to redesign our whole chip. So the protocols here got a lot more standardized and uniform and flexible than before. But in exchange, we get to transfer data very quickly between the processor and the memory controller. We can make the memory controller now very smart and then access memory in a more efficient way.